Okay, so this is the first in our series of videos on transformations of functions. This is, I think, a really important part of the course. It comes up in various areas, probably in isolation. It'd only be a handful of questions, but knowledge and understanding of transformations is really important to your understanding of all the different functions and being able to work with them effectively. I'm going to detour away from the textbook in this unit and restructure things in a slightly different way. And I'm going to start from where you should be familiar. So when we introduce a whole lot of graphs through Unit 1 and 2, we tend to just establish how the different numbers in the function affect the graph just through observation. We see that, when we change that number there, the graph goes up, or when we change that number there, the graph goes sideways, left or right. But we don't actually tend to kind of formalize that, and we certainly don't go right back to grassroots to see kind of why that happens to the equation. So I'm going to start from where we're comfortable, where we should be familiar in terms of looking at a function and being able to identify, that number does this to the graph. Okay, and so we're going to be starting from that point of function notation. Now, in my experience, most students don't actually have strong enough algebra skills to be able to accurately deal with transformations when things get slightly more difficult if they only ever work in function notation. And so the remaining videos after this, the next sort of 3 videos, will be going back to sort of first principles of transformations and understanding why, f of x minus 3 moves the graph to the right by 3 even though you're subtracting 3 and those sorts of things. Being able to see the algebra of that and starting right back from the beginning. And in my experience, actually, that offers a more foolproof way for you to both apply transformations to functions, but also in particular, to determine an accurate sequence of transformations. But let's start from where we're familiar. So many graphs can be described as transformations of other graphs. So essentially, once we then know our basic shapes, together with our transformations, we can draw a really wide range of graphs. And a transformation is a mapping. You'll often hear this phrase, mapping. Apologies, let's just bring back the CAS. A transformation is a mapping from R2 to R2. You'll see this as well, particularly when we get to sort of matrices and transformations, the way those are sort of written out. And all that's saying is that we are mapping one point that's in R2, R squared really, R squared being, the real numbers by the real numbers, so the Cartesian plane. So any point in R squared maps to another point in R squared under some kind of transformation, whether that's a translation, whether that's a dilation, whether that's a reflection. The function or point that results after the transformation is called the image of the original function or point. Okay, and sometimes we can talk about the pre-image, but in all honesty, that's not very common language. So as I said, to date we've learned about transformations in a fairly informal manner, simply coming to recognise patterns in graphs and functions. And we deal with 3 types of transformation. We're not changing that this year: dilations, reflections, and translations. It's really important when you're talking about transformations that you use the right language. Okay, we don't talk about shifting or stretching or moving. We talk about a dilation, we talk about a reflection, we talk about a translation. Okay. When you're dilating something, again, you must make sure that you're able to describe the dilation fully. So you can't say to someone, take that graph and dilate it, because that's not enough information for them to actually be able to execute the instruction. Even if you were to say dilate it by a factor of 2, that's still not enough information because you haven't indicated in which direction the graph should be dilated. So dilation needs to be described in terms of both the size of the dilation, how much you're going to stretch by, but also the direction of the dilation. Reflections, we need to know which line we are reflecting in, and also language. I find often students tend to write, reflection from, or reflection, or they talk about dilation in the x-axis. So dilation is a stretch. You're not stretching in something, you're stretching away from something, or in the direction of something, or parallel to something. Okay, so getting the language right. When you're reflecting, it's like a mirror. You don't look at your reflection on the mirror, you don't look at your reflection from the mirror, you look at your reflection in the mirror. Okay, and we reflect a graph in a line, in the x-axis, in the y-axis. is really the only reflections we deal with in this course. Also, we do deal with reflection in the line y equals x when we talk about the inverse function. We don't tend to talk about that too much as a transformation. And then translations, again, you need to know how much you need to translate by and in which direction you need to translate. So from the x-axis, we might say left or right, up or down. Those are perfectly acceptable words to use. You'll see the textbook often uses things like in the positive direction of the x-axis, meaning to the right. In the negative direction of the y-axis, meaning down. You don't need to say that. You can say left and right and up and down, okay? But you also need to be able to understand what is being said if a translation is in the negative direction of the x-axis, for example. Okay, so let's just have a quick look at the 3 different transformations, but we can also do them each in 2 directions. So we've sort of got 6 transformations we're dealing with here. Over on my CAS, I've sort of just got a graph set up here so we can sort of see this in motion rather than in the static diagram you can see on the page. So when we dilate something from the x-axis, we're stretching away from the x-axis, so in this direction, okay? So often when students begin to learn about parabolas, for example, and they learn about, y equals 2x squared versus y equals x squared, they talk about it being thinner or narrower, and it does result in a thinner or narrower shape, but that's misleading in terms of the direct transformation that's happening, because it's not actually about being dilated that way. It's actually about the 2 out the front here. Well, here actually it's a 3, sorry. So the 3 out the front here is stretching by a factor of 3 in this direction. So it's all the y values that get multiplied by 3, okay? Every y coordinate on every point in the graph gets multiplied by 3, and consequently we get this taller, thinner graph because it's been stretched in a vertical direction. So you can see that over here on the CAS. I've got y equals x squared is the black graph, which is sitting under the red graph. You can't see it right now. And y equals a times f1 of x, so that's a times x squared. So as I increase a, we're going to see, sorry, it's hard to navigate with my pen here. Let me do it this way. We see that the graph gets thinner, but actually what's happening, I'll talk about that one in a second, actually what's happening is that the graph is being stretched by a factor of, well in this case this is 5, so this is 5x squared, so we can see that there was a point here at 1, 1, and now on this graph there's a point here at, sorry I can't go near it without highlighting it, there's a point at 1, 5. So the y values have all been multiplied by 5. The point that was at 2, 4 would now be at 220, so that's right up the top up here. So it's been multiplied by a factor of 5 away from the x-axis. We can also have a look at the reflections while we're here, reflections from the x-axis. Actually, before we get to that, so if a is a number less than 1, okay, we're multiplying, or here in this case, we're multiplying all of the y values by 0.2. So the graph has been squashed down closer to the x-axis, okay? Every y value, so instead of going through 1, 1, it now goes through 1.2. Instead of going through 2, 4, it now goes through 2 and whatever 0.2 times 4 is. So that'd be 0.8, okay? So we get this squashing down. Obviously, if a were to equal 0, we actually don't have a quadratic function at all, so that's not to be considered. But if a becomes negative, the graph is now, so here's a equals -1, the graph is now reflected in the x-axis, okay? So -1 times f of x would reflect the graph over the x-axis. If it was negative, 2, let's just see if we can get there, -2 times f of x, there's 2 different transformations that have happened there. You can't dilate by a factor of -2. It's a reflection in the x-axis, that's the negative, and it is a dilation by a factor of 2, which makes it sort of taller and thinner, having stretched away from the x-axis further. Okay, so that's our dilations from the x-axis. We can obviously also, the same thing happens no matter what the function is. So I've used y equals x squared as an example, but if I were to change, go back up the top here, if I were to change that to x cubed, for example, the same thing happens. We make a bigger, the graph stretches away from the x-axis. We make a less than 1, it squashes towards the x-axis because all the y values are being multiplied by a fraction. We make a negative and the graph reflects in the x-axis. Okay? Alright, so let me just change that back to x squared before I go across to the next transformation. Okay, so then if we ever think about the dilations from the y-axis, so that's when we have, actually let me just make the colour of this graph different. so we can actually see it. Okay, so originally y equals x squared is going to sit underneath, it'll stay still so we can compare to it. And then we're looking at f of nx, okay, so in this case that is, we're looking at, let me just write over here, we're looking at y equals nx all squared, so a number in here. And the key thing here is that if we have a look at what happens as I make n bigger, the graph gets narrower. So this is about dilation from the y-axis, but as n gets bigger, the graph gets narrower. So let me see, I've made n, let me make n 2. If I can hit it, not quite there. Okay, so if n is 2, what's actually happened here, if we look at the points, and it's going to be a little hard to tell, but the original graph goes through 1, 1, the dilated graph goes through 1, half 1. The original graph goes through 2, 4, the dilated graph goes through 1, 4. The original graph goes through 3, 9, the dilated graph goes through 1 1/2, 9. The original graph goes through 4, 16, the dilated graph goes through 2, 16. So all of the y values have been halved. If the n value is 2, so y equals 2x squared, the 2 is a dilation by 1/2 from the y-axis. Okay, so we use the reciprocal of that number is the dilation factor. So you'll see then what happens is if I make n a fraction, so for example there n is 0.6, actually let me just make it 0.2, it's negative, I don't want that, there. Okay, so if n is 0.2, we've got y equals 0.2x squared. I can't work in fractions in the calc, that's 1/5 x squared. Okay. Now what's actually happened is a dilation by the reciprocal of 1/5, which is 5 from the y-axis. So the graph's been stretched out away from the y-axis by a factor of 5. So instead of going through 1, 1, it now goes through 5, 1. Instead of going through 2, 4, it now goes through 10, 4. Okay, and it's a wider graph dilated by the reciprocal of that number from the y-axis. Okay, again we would see the same thing happen if we change the original function into a cubic or a quartic or a hyperbola or whatever it might be. The effect is to dilate the graph by a factor of 1 on n from the y-axis. Similarly, if we make n negative, so actually I'm going to alter the function. Let me put n back to 1 for a minute. Just type it. Okay, if I alter the function back up to, let's make it x cubed. Okay, again we see the same things happening, so as n gets bigger, it's actually squashing in towards the y-axis, dilated by a factor of 1 over that number from the y-axis. If n's a fraction, it becomes wider because it's dilated by a factor of 1 over 0.4 in this case. So 0.4 is 2/5, so it's dilated by 5 on 2 or 2 1/2 from the y-axis. And then what we see is when we make a negative, sorry not a, when we make n negative, the graph has been reflected in the y-axis. Okay, so if we have y equals negative x all cubed or negative x all squared, and that's why we couldn't see it when we did the quadratic, because negative x all squared is x squared, because when we reflect in the y-axis nothing changes, whereas the cubic is going to, that shape reflects in the y-axis when we make n negative. So if n's a negative value, if we have y equals negative 2x cubed, it's going to be reflected in the y-axis and dilated by 1/2 from the y-axis. Okay. Alright, let's change back to the quadratic for a minute again and have a look at the translations. So we've looked at the dilations and the reflections with n and a. Back to 1. Let's have a look at the translations. So let's have a look at f of x plus h. Okay, so what we see here is if I make h bigger, okay, so I make h1, h2, h3, so now that's f of x plus 3. The graph hasn't gone to the right by 3, the graph has gone to the left by 3. And what we can sometimes kind of think about loosely is that if the transformation, if the number change or the effect on the function is happening inside the function, it's it's the opposite of what we think it should be. So as we said, f of 2x is not a dilation by 2 from the y-axis, it's a dilation by half from the y-axis. Okay. F of x plus 2 is not going to the right by 2, it's going left by 2. And when we get into the first principles, looking at the algebra of this right back from the beginning, we'll sort of see why they end up being backwards, whereas the other things, so f of, a times f of x, that's just a dilation by a factor of a. 2, that's just dilation by a factor of 2, it's not backwards. When we get to looking at the translations going up and down, if we add 2, it goes up. That's not confusing at all. But the things inside the function, they're often the backwards of what we think they should be. Okay, so obviously then, obviously then when we make h smaller than 1, smaller than 0, sorry, so if h is negative 1, so we've got f of x minus 1, we go to the right by 1. F of x minus 2, f of x minus 3, f of x minus 4, etc. Okay. If we look at the vertical translations, k is 0. As we increase k, the graph goes up. Okay, nothing tricky there. As we decrease k, the graph goes down by that factor. So we use the right words. Translation up by 1 unit. Translation up by 2 units. Translation down by 3 units. Okay. Alright, so they should be fairly familiar, given that we've worked through a lot of functions over the course of, Unit 1 and 2, and perhaps before that with the parabola in simpler graphs. So here they are all summarised. A times f of x has been dilated by a factor of, now I've written the modulus of a, because the modulus, we don't no longer do the modulus in this course, which is a bit frustrating because actually it was quite useful. But the modulus of a simply means it doesn't matter whether a is positive or negative, it's always a positive value. So for example, the modulus of 2 is just 2, the modulus of negative 2 though is also 2. So the point of that then is that we're not the dilation factor is not, if this was negative 2, the dilation factor is by 2 from the x-axis. Okay. Similarly, if we have f of nx, f of x has been dilated by a factor of 1 over the modulus of n, so just take the positive value of n from the y-axis. If a is negative, that's because we've got reflection in the x-axis, that's here, negative f of x. If n is negative, then that's because we've got a reflection in the y-axis. F of x plus h is if h is a positive number. If we're adding, we're going to the left by h units. F of x minus h, if h is a positive number, means that we're subtracting a number from x and we're going to the right. So remember, sort of backwards. So these things that affect that are inside the function, the reflection not so much, because it's just negative 1. The reciprocal of negative 1 is still negative 1. But certainly the dilation from the y-axis and the translations left and right, it is sort of the opposite of what you think it should be. Okay, it's not dilated by n from the y-axis, it's 1 on n. It's not going right by h when you add h, it instead goes left. Again, when you subtract h, you would think you would go left, but you don't, you go right. Okay, so you need to think carefully about those ones. F of x plus k translated up by k, and f of x minus k translated down by k. Okay, so let's have a look at some examples. In each of the following, state the transformation or transformations that it takes function 1 to function 2. Okay. So if we have y equals x cubed, changing to y equals negative 5 times x cubed, there's 2 transformations happening there. There's the negative out the front, which is reflection in the x-axis. Okay, and then there's the 5, which is dilation by factor 5 from the x-axis when it's outside of the function. Okay, so 2 transformations. Now it wouldn't matter which order we listed those in. Okay, and that's because if you have x cubed, and you multiply it by negative 1 first, and then you multiply it by 5, actually it's the same as if you multiply by 5 and then multiply by negative 1. It doesn't change the function. Okay, next, in the second one, part B, we're going from y equals root x to y equals square root of 2x. Okay, so if this is y equals f of x, this is y equals f of 2x. The x part of the function has been replaced with 2x. Okay, Whereas this one up here, the previous example, part A, let me just write in there so we can see. If this was y equals f of x, then this is y equals negative 5 times f of x. Okay. Alright, so if we go from f of x to f of 2x, that is a dilation by factor, by factor 1/2, the reciprocal of 2, from the y-axis. Okay. Alright, now C we could think about in two different ways. If we think about this as y equals f of x, then this is y equals f of 3x. Okay, we've replaced the x part of the function with 3x. Okay, x part of the function with 3x. And so that is a dilation by factor 1/3 from the y-axis. Alternatively, you could think about that as being y equals 1 on x becomes y equals 1 on 3x is the same as 1/3 times 1 on x. So we could actually think about it as being y equals f of x becomes y equals 1/3 times f of x. So it could also be described as a dilation by factor 1/3 from the x-axis. It's really important that we understand that these two transformations aren't the same thing for all functions. It just so happens that for this particular function, for the hyperbola, if you were to dilate by a factor of 1/3 from the y-axis, you would actually end up with the same graph as if you had dilated by a factor of 1/3 from the x-axis. But it's purely because of the function type that it's a hyperbola. If this was a quadratic, for example, dilating by a factor of 1/3 from the y-axis would mean getting 3 times x squared, which is 9x squared. Oops. Whereas dilating by a factor of 1/3 from the x-axis would be 1/3 times x squared, and these aren't the same thing. Okay, so you can often describe transformations in more than one way, but it's not to say that they are the same for all function types. Okay, finally here in part D, we've got a truncus. So if 1 on x squared is f of x, we now have 1 on x minus 4 all squared plus 7. Okay, so we've replaced the x with an x minus 4, which means it is f of x minus 4, and then we've stuck a plus 7 on the end. So that's the function that we've got there. Okay, so we know that f of x minus 4, that's a translation to the right by 4. Okay, and then the plus 7 on the end is a translation up by 7 units. Okay, again, the order that we apply those doesn't matter. If we took the truncus and added 7 to it and then replaced the x with x minus 4, it would still result in the same function. Okay, it's to do with the fact that those two translations affect different coordinates. So moving the graph to the right, or translating the graph to the right by 4 units, is altering the x coordinates of the points, and translating the graph up by 7 units is altering the y coordinates of the points. So because they don't interfere with each other, we're not affecting the same coordinate. It doesn't matter what order we do them in, it's going to have the same result. Okay, whereas sometimes if you apply multiple transformations that affect the same coordinates, it matters the order that you apply them in, and that's what makes this tricky. Okay, so let's have a think about that in this example here. So as I said, many functions are the result of applying more than one transformation, but we must take care with the order that the transformations are applied. So here below we have the graph of y equals x squared. Draw the image of this graph after it has been translated up and then reflected in the x-axis. Okay, so if we think about, if we translate it up, translate up by 2, if we translate up by 2 units, if you take every point and go up by 2 units from where it currently is, right, that's going to be a bit off the chart there. So essentially, sorry, I've got this really fine pencil. So that's the up by 2 units, because that's not my final answer. And then if we reflect it in the x-axis, it's going to come down to here it's going to come down to here and down to here. That's 2, 6, so it becomes 2, negative 6, and negative 2, 6 becomes negative 2, negative 6, and then that's 3. It's actually off the chart, it's actually down here. Alright, so our graph would look like that if we translated it up by 2 and then reflected it in the x-axis. Whereas over on the right here, if we reflect the graph in the x-axis first and then translate it up by 2, so reflecting it in the x-axis is going to move it down here and then take it up by 2, okay? That point goes up by 2. This point's at 1, negative 1. Up by 2 brings it back to 1, 1. Negative 1, up to here. Sorry, I drew a very rough reflected parabola, but reflected it would be at 2, negative 4, and then up by 2 takes it to 2, negative 2. Negative 2, negative 4, and then up by 2 is negative 2, negative 2. What have we got? So that is at 3, 9. Reflecting in the x-axis is 3, negative 9. Up by 2 is 3, negative 7. Okay, and same with the negative 3, negative 7. Alright, so what we did here on the left, we translated up by 2 and then reflected in the x-axis. On the right, we reflected in the x-axis and then translated up by 2, and the result is 2 different graphs. So the point is that it matters the order that you apply the transformations in. And if you're being asked to state the sequence of transformations, it matters what order you state the sequence. Okay, it's really important that you understand that. So if we think about the algebra of what's happening here, if our original function, actually let's go, yeah, if our original function is y equals x squared, and the first thing we do is translate it up, we know that translating up makes f of x become f of x plus 2. So that's simply going to mean we do y equals x squared plus 2. Okay, and then we reflect in the x-axis. Now we know that means that f of x becomes negative f of x. Now the thing is that this is now the function that we're translating in the x-axis. That whole thing is f of x. So if we want to then make it negative, it is negative all of that, which means we get negative x squared minus 2, which is what we're seeing on the left. Whereas on the right, if we started with y equals x squared, and the first thing we did was the reflection, so we know that means f of x becomes negative f of x. So that would be y equals, negative x squared, okay? And then we translate it up by 2, or f of x becomes f of x plus 2 when we go up by 2. So we take our existing function, which is that, and add 2 onto the end of it, okay? So it becomes negative x squared plus 2. And these are not the same. Okay, so the order that you do those two things in. So in the first example, we added 2 and then multiplied by negative 1. In the second example, we multiplied by negative 1 and then added 2. And that creates 2 different things, all right? If you take something and you add 2 to it and then you multiply it by negative 1, it's not the same as taking something and multiplying it by negative 1 and then adding 2 to it, okay? All right, so let's have a think about some more examples. So find the image of f of x equals x to the power of 5 after dilation of 2 from the x-axis, followed by translation 3 to the right, and 4 down. Okay, so let's just go one step at a time. So if f of x is x to the power of 5, the first thing we do is to dilate by 2 from the x-axis. So that's going to mean f of x equals 2 times x to the power of 5. Then we translate 3 to the right, so that means replacing the x. So remember, so dilation by 2 from the x-axis is 2 times f of x. Translation 3 to the right is f of x minus 3, and 4 down is f of x minus 4. Okay, so now we're doing this. We're taking the x in our existing function and replacing it with x minus 3. Okay, and so our function becomes, actually, they're not all the same thing, so they can't all equal f of x. We're going to start with that. It becomes that, and it then becomes 2 times x minus 3 all to the power of 5. And finally, we subtract 4 from the whole thing to translate down by 4. So 2 times x minus 3 to the power of 5, take away 4. And there's our final function. Okay, B, find the image of f of x equals root x after translation left 3 followed by dilation by a factor of 1/5 from the y-axis. Okay, so translation left 3 is f of x plus 3. Dilation by a factor 1/5 from the y-axis is f of 5x. Okay, so we want to start with y equals root x. We then want to do this to it, which is to replace all the x values with x plus 3. Okay, so it's going to become y equals root x plus 3. And then this is where things get tricky, and this is where I find quite often your algebra skills aren't always strong enough to recognise the difference and to be able to execute this correctly. So now we're going to take our existing function, having done the translation left by 3, so focused only on here, and we're now going to apply this transformation, which means we replace the x values in the function with 5x. So we're not multiplying the whole thing underneath the function by 5, we are replacing x with 5x, okay? So what we have here is that f of x is equal to square root of x plus 3. So if we replace x with 5x, we're just replacing the x. So it is square root of 5x plus 3, not 5 times all of x plus 3, okay? So it's square root of 5x plus 3. So we've just replaced the x with a 5x. So here we replaced x with x plus 3, then we're replacing the x with a 5x. Okay, and so that's our final function at the end there. Find the image of f of x equals 1 on x after translation up by 4 followed by a dilation of a third from the x-axis. So translation up 4 is f of x plus 4, and then it's a dilation by a third from the x-axis, so that's a third times f of x. Okay, so if we start with 1 on x, we're going to translate it up by 4, that's 1 on x plus 4. And then we're going to do this final translation, which is to take a third and multiply a third by the whole function. Sorry, not final translation, final transformation, which is a dilation. So doing a third times the whole function. So we're taking our whole function as it is currently and then multiplying it by a third. Okay, so that's what's got to happen. So you're not multiplying the original function by a third because you've applied your translation first, then you're taking that thing and doing a third times all of that. Okay, so it'll be 1 on 3x plus 4 on 3. Okay, that will be what you'll get wrong if you apply them in the wrong order. You'll have plus 4 still there instead of plus 4 on 3. So multiplying the whole function. After the last translation, you've now got a different function, taking that whole function and multiplying it by a third. Okay, D. Find the image of f of x equals x to the negative 4 after translation left 7, followed by reflection in the y-axis, followed by dilation of factor 3 from the y-axis. Okay, so translation left 7 is f of x plus 7. Then we reflect in the y-axis, which is f of negative x. Then we dilate by a factor of 3 from the y-axis, which is f of a third x. Okay, so this is really important that we get this right because all three of these things are happening inside the function. They're going to interact with each other differently depending on the order that you do them. So the f of x plus 7 is the first thing, then the f of negative x, then the f of a third x. Okay, so if our original function is x to the negative 4, the first thing we're going to do is f of x plus 7, so we're going to replace the x's with x plus 7's, so it becomes x plus 7 all to the power of negative 4. The next thing we're doing is the reflection. We're going to replace the x's in the function with negative x's, so it becomes y equals negative x plus 7 to the negative 4, or we could write that as 7 minus x to the negative 4. And then the next thing we're going to do is the dilation by 3 from the y-axis. And so again, we're replacing the x part of the function with a third x. Okay, so just the x part of the function replaced with a third x. So y equals 7 minus 1/3 x, or x on 3 to the power of negative 4. Okay, so it's really important that you understand how the function notation works and that you can understand the difference between, f of a third x versus a third times f of x, and all of those things. Okay, then the last thing we might need to do here is to work backwards and determine the sequence of transformations. So again, this is where I think once we go back to basics over the next couple of videos, I genuinely think that that's easier for most of you because it involves a little bit more algebra, but the algebra is a bit more routine. So if you're going to try to identify the sequence of transformations, you can always describe the sequence of transformations in more than one way, okay? But when we're working from function notation, it's much, much easier if you set things up in a way that you always describe them in a particular order. Some people talk about this, and that is going to be dilations and reflections and then translations. Some people talk about this idea of Dr. T. I really don't like it because you don't have to always describe the transformations as the dilations and then the reflections and then the translations, okay? Particularly when we get into the alternative way of doing this, you'll see actually, there's lots of different ways we can describe them, and there's nothing that says you have to describe it this way. However, if you are going to always try to work from function notation, if you want to focus on getting your function into a fairly standardized form, and then once you've done that, once you've got it into this standardized form, then the correct order from that form is that it's the dilations first, and then the reflections. Well, technically they can go in either order, but then the translations come after the dilations and reflections. And this is the easiest way to deal with it when you're in function notation. So you want to try and get it in this form. You want to have A, so that's your dilation from the x-axis and your reflection from the x-axis out the front of your function. And then in the function you want to factor out the n, that's often the trickiest bit, which is both the dilations from the y-axis and the reflections in the y-axis, so that then you can correctly get your translation up or down, and you want your plus k also to be independent of a. So you don't want this, okay, that wouldn't be right. You want to have a times your function plus or minus k, and within the function you want to have n brackets x plus or minus h. So the tricky thing is, and this is where I think lots of students fall down in trying to rely on this method, is that your algebra is actually not often strong enough to be able to recognise whether or not that you're in that form. So in this case, we're not in this form, okay? This plus 5 here, that's not a translation left or right because it's not in the squared. The function is something squared. This isn't some x plus 5 all squared, okay? It's not a translation left or right. It's x squared plus 5. So it's a translation up or down. But the problem is you've got it intertwined with, you've got the k intertwined with the a in this particular version. So what we need to do first is to expand out that bracket and write it as 3 times x squared plus 5. And now we can see that our original function was x squared. So if this is y equals f of x, this function was y equals 3 times f of x plus 5, which is not in that form. And now what we've got it as is 3 times f of x plus, sorry, it shouldn't be plus 5, I didn't actually expand it, did I? Plus 15. Plus 15. Okay, so now that's your a. Oh, sorry, that had diameter. That's your a, and that's a k. There's nothing else. There's nothing happening inside the function. There's no n or h. Okay, so our sequence is dilations and reflections first. So dilation by a factor of 3 from the x-axis, it's outside of the function, and then the plus 15 is translation. You must use the word translation, up 15 units. Okay. Alright, so this second one here, if x cubed is f of x, then what we have here is f of 2x plus 4 all cubed plus 5. Okay, so what we've got here is the plus 5 is a plus k. There's no a, okay? However, one of the issues we have here is in the function here, we've got our n value not factored out, okay? So you must factor out the coefficient of x must be factored out, even if it means creating fractions, but it must be factored out if you're going to correctly read off the translations and reflections, okay? So what we actually need to do is write this as f of, sorry, not, if we're to correctly read off the translation, we have to have the n value factored out. So it has to be written as 2 times x plus 2, all cubed, plus 5. Okay, and so now we've got our plus 5 value still out here. We've got our n value here, and we've got, sorry, our plus 2 is h. Okay, so if you didn't factor that out first, you won't correctly read out, you won't correctly give the correct sequence of transformations. Okay, dilations and reflections first. So that dilation, the n value is what's first there. So it's a dilation by a factor of 1/2 because it's a reciprocal from the y-axis. And then the 2 and the 5 are our translations. So translation, the plus 2 in the brackets is left by 2 units. And the plus 5 at the end is up by 5 units. They can happen in any order, the two translations. What's key is that that dilation must be listed before the translations. Okay, part C. If we have a think about this as y equals f of x, what we currently have here is y equals, now that 2, that's 2 times 1 on 1 minus 3x. Okay, so what we have here is 2 times f of 1 minus 3x. Okay, so once again, the issue is this, the coefficient of x must be factored out, okay? So we must write this as 2 times f of negative 3. As I said, even if it means making fractions, it's now going to be x minus a third. Okay, so now we can correctly read off. We have our, this time we have an a value out the front, which is 2. We have an n value as well, which is negative 3, so there's both a reflection and a dilation there. And we have an h value in here, which is minus 3. Okay, so we have our read of our dilations and reflections first. So we've got dilation by, I haven't left us a lot of room here, sorry, factor 2 from the x-axis. We've then got dilation by a factor of 1/3 from the y-axis. We have also a reflection in the y-axis. And then finally we have our translation to the right, sorry. So when we subtract in there, we're going to the right by 1/3 of a unit. Okay, so you've got 1, 2, 3, 4 different transformations in that order. The dilations and reflections, the order here could alternate around, but the translation must happen after those dilations and reflections. Okay, finally here, if we've got y equals root x, if that's f of x, then that has become y equals 1 minus 2 times f of 2 minus x. Okay. Now let's just write this in a slightly different order. So this is negative 2 times f. Now again, we've got a coefficient of x here that isn't 1, and so that must be factored out. So I'm going to write that as negative x minus 2. That's going to allow us to get those transformations correct, and then I'm going to write that as a plus 1. So we have got a bit of everything here. We've got our negative 2 out the front. That's our a value. Okay. We've got our negative 1 in here. That's our n value, so that's a reflection in the y-axis. We've got our minus 2 here, which is our translation left and right. I'm going to need a new highlighter colour. And then we've got a plus k on the end, a plus 1 on the end, which is our plus k. Okay, so we've got lots happening here. Let's list them out. So we've got a dilation by factor 2 from the x-axis. We've got our reflection in the x-axis. That's the negative out the front, but we also have a reflection in the y-axis. Could probably have listed them at the one point, reflection in the x and y-axes. Then we've got the minus 2, x minus 2 in the bracket, so that's a translation to the right by 2 units. And then finally we've got our translation on the end, translation up by 1 unit. Okay. So practice makes perfect. You've really got to focus on understanding how to make sure that you're in this correct format before you list off your translations, transformations, listing dilations and reflections first, and then followed by translations. We'll have a look at an alternative method over the next couple of videos, which rely less on you being able to clearly reformat the answer in that function notation. However, this is more efficient if your algebra is strong enough to be able to do it this way and do it reliably and get it correct reliably when you do it this way. Alright, example 4, I suspect this is probably the last one, yep. Show that 4x minus 3 over x plus 1 is equal to 4 minus 7 over x plus 1, and hence determine the sequence of transformations that maps y equals 1 on x to y equals 4x minus 3 over x plus 1. Okay, so show that this relationship is true. You either start with the left-hand side and turn it into the right-hand side, or you start with the right-hand side and turn it into the left-hand side. You don't jumble things around when you're doing a show that. Okay, so I'm going to have our left-hand side is equal to 4x minus 3 over x plus 1. We've done this technique before. I've talked about it before. It sort of loosely is partial fractions for those of you who do specialist maths, but you actually don't need it to be that complicated. The key thing is here, I don't want any x's in the numerator of the fraction, so I need to be able to cancel x out of the numerator, and the only way I'm going to be able to do that is if there is an x plus 1, so that it will cancel with the denominator. So I start by writing x plus 1 in the numerator. That's what I want, and so I put it up there. And then I work around it to adjust. So there'll have to be a 4 out the front here so that I get 4x. But if I put a 4 out the front there, when I expand out that bracket, I then have 4x plus 4, and I want minus 3, not plus 4, so I'm going to have to take away 7. Now I can split this into two fractions. That's 4 times x plus 1 over x plus 1. Take away 7 over x plus 1. And the x plus 1s will cancel, which means it is 4 minus 7 over x plus 1, which is the right-hand side. And so I have shown that that relationship is correct. Then it says, hence determine, so hence meaning use what you've just learnt here, determine the sequence of transformations that maps y equals 1 on x to y equals 4x minus 3 over x plus 1. Okay, so we're going from y equals 1 on x to y equals 4x minus 3 over x plus 1. Now, we've just shown in the first part that y equals 4x minus 3 over x plus 1 is y equals 4 minus 7 over x plus 1. I'm going to write that as negative 7 on x plus 1 plus 4. Okay, so what we actually have here is, if we think about this as being y equals f of x, 1 on x, that has become y equals negative 7 times f of x plus 1 plus 4. And so that's in that nice standard form. We've got our a value, we've got our h value, and we've got our k value, and so we can state our sequence of transformations. So it is reflection in the x-axis, that's at negative. We've got a dilation by factor 7 from the x-axis. We've got a translation left by 1. And we also have a translation up by 4 units. Okay, so the work today is from a worksheet at the back of your booklet, transformations using function notation.